Greetings everybody. So today we are going to discuss about the concentration units. First and foremost, we need to understand what is concentration. The term concentration basically indicates the amount of solute. Whenever we are discussing some characteristics of any particular substance, particular material, particular compound in chemistry, we discuss their characteristics. Here, when we discuss the characteristics of solution, when we discuss the characteristics of solution, then we discuss the characteristics of solution in terms of concentration. Such that if we have concentration, we can define concentration as the amount of solute which is dissolved per unit volume of the solution, or amount of solute dissolved per unit decimeter cube per unit volume, or per unit centimeter cube of the solution, right? So per unit volume of solution. Now unit for concentration can vary from, you know it can vary based on different concentration units. First, a concentration unit which we are going to discuss about is percentage composition. And first percentage composition is weight by weight composition, such that whenever we take concentration, whenever we take percentage particularly, so what we actually do is that we take the obtained numbers up out of total numbers and multiply it by 100 in order to get the percentage. So in that way we are also going to do the same. We are going to take the obtained, we are going to take the divided by solute divided by solution solute divided by solution into 100, due to which it will give us the percentage composition. Likewise, we can also write it in that manner: solute is is a part of solution, or solute is a part of solution, due to which we can write it as the smaller part which is written in the numerator, and larger part solution which is written as a denominator, due to which solute divided by solution into 100. Or in other words, we can also write it as solute divided by solvent into 100, right? And after that, when it comes to both considerations, we are going to discuss it by examples. When it comes to weight by weight percentage composition, weight by weight percentage composition shows us that we are going to divide the weight of the solute by weight of the solution. Weight of the divide divided by weight of solution into 100 will be equal to weight by weight, right? And if we talk about, let's suppose we have solute which is, we have 10 gram of solute, and that is dissolved in 100 gram of water solvent. Sorry, so there's 10 gram of solute which is dissolved in 100 gram of solution. Please remember the word solution. So 10 gram of solute dissolved in 100 gram of solution would be written as 10 by 100 into 100, due to which solution will become 10%, right? But if we talk about solute weight by weight percentage of solute and solvent, then at that moment we'll take 10 gram of solute, and then we'll take the weight of solvent, not the weight of solution. Rather, in this case, what we are going to do in order to find weight of solvent, we are going to either we'll be given the particular weight of solvent, or in case if you are not given the weight of solvent, so in this case weight of solvent can be written as in ideal condition. Whenever there is an ideal solution, so weight of solute can be weight of solvent in terms of weight of solute can be expressed as 100 minus 10 is equals to 90, right? So in this case 100 was the weight of solution and weight of solute was 10, due to which we got the answer which is 90. So this answer 90 was due to the, and this answer 90 basically shows the weight of solvent, and that is basically obtained in a condition whenever there is an ideal solution. If there is a non-ideal solution, then this condition will not persist. So 100 divided by 90, and when we are going to divide it by 90 and then multiply it by 100, it will cost to give us a concentration, and that concentration obtained would be around 11.11%, right? Into 100, right? Let us try with this as well. And this is how we obtain the percentage. Likewise, if we talk about other concentration percentage composition, we can take weight by volume of the solution. Now in weight by solute and weight by solution, we are not having any unit, and uh, weight divided by volume, weight of solute divided by volume of solution. Let's suppose if we have weight of solute which is 10 gram, and volume of the solution is 100 1 decimeter cube, right? So when you're going to multiply it by 100, So it will become as, 1000, right? It will become as 1000%. But since we are taking the concentration in centimeter cube, we do not need to write it in terms of thousand. We are going to write it in terms of hundreds. Let's suppose we have 100 centimeter cube. We're going to write it in terms of centimeter cube. 100 centimeter cube, and the answer obtained would be 100 centimeter cube into 100, which is 100 divided by 100. 100 cancel, and answer obtained would be 10. So 10% would be the solution or percentage composition concentration, which would be the weight by volume concentration, right? And in this case, we have the volume of solution is known, volume of solute is unknown, right? And after that, when it comes to weight, volume of solute divided by weight of solute, volume of solute here is considered under the case volume of solute is 10. Let's suppose if we take volume of solute equal to 10 centimeter cube, right? Now in this condition, the third case, we are having the volume of solute, but we are not having the volume of solution or volume of solvent. So 10 centimeter cube taken divided by 10 centimeter cube divided by 10 centimeter cube divided by, let's take weight of the solvent, let's take 100 gram, right? If you're taking 100 gram, so in this case, answer obtained would be this, and into 100, sorry, into 100, right? So 100 divided by 100, 10 centimeter cube would be the answer, right? So after that, when it comes to volume by volume, again volume of solute divided by volume of solution, due to which here a common thing which I would like to highlight is that here volume of solute and volume of solution are, both of these are known, but the volume of solution is not the algebraic sum of volume of solute and volume of solvent. In cases the examiner mentions that this is going to be an ideal solution, then we can consider volume of solute plus volume of solvent is equals to volume of solution. Otherwise we cannot consider it in that way. Moreover, when it comes to molarity, molarity basically is defined as, it is another concentration unit, in which we are going to consider the amount of solute. Let's suppose we take amount of solute, we are going to take amount of solute in grams, amount of solute in grams, not, sorry, not in grams but in moles, because mole is basically in actual the amount of the substance expressed in grams, even though uh, that is expressed in AMU, but when from the AMU, when it is converted into grams, that is considered as 1 mole. So in that case we can also take it as a unit of its matter, but amount of solute would be in moles, and that would be the concentration, right? So amount of solute in moles divided by 1 decimeter cube of solution per unit volume of solution, or 1 decimeter cube of solution, or 1 centimeter cube of solution. 1 decimeter cube of solution is the SI system, right? Amount of solute in moles divided by 1 decimeter cube of solution. Let's suppose if we talk about uh, a solution which I want to produce molarity of 1 molar solution, it is represented by capital M. 1 molar solution represented by capital M. 1 molar solution of sodium hydroxide. So in this case, if I want to produce 1 molar solution of sodium hydroxide, I need to take 1 mole of sodium hydroxide. 1 mole of sodium hydroxide is equals to 40 gram, right? And when we are going to take 40 gram of sodium hydroxide and dissolve it in 1 decimeter cube of water, if I'm going to dissolve, you know, 40 gram of NaOH sodium hydroxide into 1 liter or 1 decimeter cube of water, 1 liter of water, then at that moment it will cause to give us a 1 molar solution of sodium hydroxide. Now there is a point to understand that if we are taking a molar solution of a larger molar mass, let's suppose if we are taking molar solution of sucrose, molar solution 1 molar solution of sucrose, 1 molar solution of sucrose will be more concentrated than 1 molar solution of glucose, because sucrose is having its higher number of molar mass, as compared to glucose, which is having less molar mass, as compared to sucrose, which is having higher molar mass, right? So will be more concentrated than glucose. Likewise, if we talk about volume of glucose due to less concentration will be more than the volume of sucrose, because volume of sucrose is less due to more concentration, due to which high volume of glucose would be there due to less concentration, and more volume of sucrose due to more volume sorry less more volume of glucose due to less concentration, and less volume of sucrose due to more concentration. Now, another factor which I would like to highlight over here is molarity is affected by temperature. So that, why is it affected by temperature? Because if we increase the temperature, then the volume of the solution increases. Volume of the solution is affected by temperature, because if volume is increased, then the attractive forces between between the water molecules are increased. Due to which attractive forces are weakened by the absorption of heat. Due to which the volume of the solution is either increased or decreased depending on the condition of the solvent, due to which it causes to give us variability in volume, due to which molarity is ultimately affected by the change in temperature. Likewise, if we talk about molality, molality is another terminology similar to molality. It is represented by small m, and here molality is given by amount of solute in amount of solute in moles, amount of solute in moles divided by amount of solute in moles divided by weight of solvent in 1 decimeter cube, amount weight of solvent in 1 kilogram, right? So amount of solute in moles divided by weight of solvent in 1 kilogram is defined as the molality, 1 molar solution of compound. Let's suppose if we have 1 molar solution of sodium hydroxide. 1 molar solution of sodium hydroxide will now be prepared in such a manner that if we take 1 molar solution of sodium hydroxide, we need to take first 40 grams, means 1 mole of uh, sodium hydroxide, and now we are going to dissolve 1 mole of sodium hydroxide into 1 kilogram of water, due to which it will cost to produce 1 molar solution. Now, if we talk about the consideration, if we compare molar solution with molar solution, then molar solution will be considered as uh, having more amount of volume within it, as compared to molar solution, which is having less amount of volume within it. Reason behind it is that molar solution basically involves the amount of solvent in liters or in volume, due to which it is an indirect comparison, indirect expression of mass with volume, due to which the amount of volume is expressed less logically. While when it comes to the molar solution is having a direct comparison of mass to mass, due to which the concentration would be ultimately less due to high amount of solvent present within the molar solution. As you can see, mole is basically what it is, the mass expressed in grams. So a mass of amount of substance expressed in grams is known as mole. So in that case, mole here would be divided by 1 kilogram of water, so it would be a direct comparison, due to which it will lead to a less concentration and high amount of volume as compared to molar solution. So in this case, we can say that molar solution is the biggest unit of concentration. After that, we are having another unit which is known as the molality. But in between both of these, we are having another unit as well, which is known as normality. Molarity is the highest unit. Then there is normality. Normality is another unit we are going to discuss. Then there is molality, and after that we are having other unit as well. Let's compose. Now these are some large units of concentration. If we talk about smaller units of concentration, we are having ppm, parts per million, ppb, parts per billion, ppt, parts per trillion. Now ppm is the most concentrated unit among the small concentration units, while ppb is less than that, and ppt is least among all, the smallest unit of concentration, ppt, parts per trillion. After that, when it comes to Some other characteristics, molality is not affected by temperature, but molarity is affected by temperature, because if you're going to increase the temperature, the weight of solvent will remain same, whether it is increasing its volume, but its weight will ultimately remain same even after heating it up. After that, when it comes to normality, it is defined as the gram. Normality is represented by n, and that is equal to gram equivalent weight, gram equivalent weight divided by the volume of solution. Gram equivalent weight divided by volume of solution is known as normality. And what is gram equivalent weight? If we talk about gram equivalent weight, it is basically the amount of weight which is the weight of a solute which is actively participating in a reaction. Now in this case, if we take gram equivalent weight of an acid, as well as if we take a gram equivalent weight of a base, as well as if we take gram equivalent weight of an element, so in this case we'll be having different gram equivalent weight. If we consider the gram equivalent weight of an acid, let's suppose HCl. So HCl basically will have its gram equivalent weight equal to the molar mass of HCl. Now what is molar mass of HCl? It is around 36.5 gram. And when we are going to divide 36.5 gram of HCl by the number of hydrogen ions HCl is having, then at that moment we'll be having its gram equivalent weight. So gram equivalent weight, molar mass divided by number of hydrogen ions in an acid. But in case of base, we'll be having the molar mass divided by the number of OH ions present within the base, right? So in this case, if we divide it by number of H ions is 1, only single H ion is present. So it would be equal to 36.5, 36.5 gram, right? After that, if we talk about H2SO4, H2SO4 is having its gram equivalent weight as the following, that it is having its molar mass 98 gram divided by number of hydrogen ions 2, due to which it becomes 47. So in this way, this will be the gram equivalent mass. After that, if we consider a base is having the same condition, molar mass divided by number of OH ions. So calcium hydroxide divided by 2, calcium hydroxide, there are 2 OH ions. So when we are going to take its molar mass, so in this case, 17, and first we need to calculate it actually. Calcium is having its mass as 40, 40 plus oxygen 60, 32 and 2, right? 74, right? 74 is its mass, and when we are going to divide by number of OH ions, which is 2, answer will be equal to 37. Likewise, if we talk about calcium only, calcium is an element. Now when we are going to take the gram equivalent mass of an element, we are going to divide the gram equivalent mass of, we are going to take the molar mass in order to find the gram equivalent mass and divide it by the valency of that element. Let's suppose calcium's valency is 2, so its molar mass is, its molar mass is 40, and then dividing its by its valency, which is 2, and 20 is its gram equivalent mass. So this is how when we are going to calculate. Now gram equivalent weight, normality is defined as gram equivalent weight divided by volume of solution. If you want to prepare one normal solution of H2SO4, so in this case one normal solution of H2SO4 will be equal to 98, um, sorry, its gram equivalent weight is 47, and 47 divided by its volume. Let's suppose if we take the volume 1 decimeter cube, right? So when you're going to take uh, its gram equivalent weight divided by 1 decimeter cube of volume, so in that case this would be considered as the one normal solution of H2SO4. Likewise, if we talk about some other solutions, we have mole fraction. Mole fraction, what is it? Mole fraction is a special unit not only for the concentration of liquid solutions, but also for the concentration of gas, solid gas, solid liquid, all types of solution, right? So if we take mole fraction here is defined as, the it is basically unitless, no unit, no dimension. and it is defined as the number of moles of solute, number of moles of a particular component of the solution. It is defined as a ratio of number of moles of a particular component of a solution to the total number of moles of the solution. If you're taking a mixture, let's suppose if you're taking a mixture in which we are having, three components. Mole fraction can measure up to two. It can measure two or more than two components present within a solution, right? So it's not a mole fraction is a solution in which we is a unit in which we can measure more than two components of the solution, right? So if we are taking, let's suppose, a solution, and in that solution we are having three components. Three components are there, and these three components have their own uh, number of moles, right? Number one component is having its number of moles. Number one component is named as A, and it is having its number of moles as Na. Number B component is having its number of moles as Nb. Number C component is having its number of moles as Nc, right? So these number of moles now would be constituting a mixture, a homogeneous mixture, which is known as solution, right? Now when we are going to divide the number of moles of a particular component by the total number of moles of the entire solution, which would be equal to Na plus Nb plus Nc, then at that moment it would be considered as a mole fraction, which means the number of moles of the solution, number of moles of the component of solution divided by the number of moles of the entire solution is known as mole fraction. And mole fraction here is basically uh, having mole fraction is can be applicable to all types of solution, can be applicable to all number of components in the solution. Now whenever we are taking mole fraction, so mole fraction of uh, all the components of a solution, mole fraction sum of all mole fractions of all components of a solution is always equal to unity. If we take, let's suppose, 1 mole, a solution of water and methanol in which 1 mole of what do we call it, 1 mole of water and 4 moles of methanol are present, right? So in this case, when you're going to take the mole fraction, water will have its mole fraction 0.2 and methanol will have its mole fraction 0.8. When we are going to add both of these, answer will be 1. And this is constant for every case, such that whenever we are taking all of the mole fractions of the component and adding them together, it will cause to give us an answer which is 1. After that, when it comes to another terminology I would like to highlight over here is about the mass, parts per million, parts per billion, and parts per trillion. Parts per billion, I've already told you which one is the highest, and first let us understand what it is all about. So parts per million is defined as the amount of solute, um, parts per million is defined as parts per million is defined as the amount of solute. Now amount of solute can be taken in weight or in terms of volume. Both conditions are applicable. So amount of solute in weight or volume divided by amount of solvent in weight or volume. Now in this case, both, if solute is being taken in weight or volume, then solution should be also taken in weight or volume. This is a condition. And after taking both of these, we are going to multiply them with hexa or 1 million, 10 is power 6, hexa 10 is power 6, right? And here this would be considered as parts per million. Now what does this equation actually signifies, that what is parts per million? Parts per million basically shows that out of, if we are taking 1 parts per million, right, 1 part per million showcases that out of 1 million molecules of the solution, there is presence of 1 molecule of the solute. Let's suppose if we take water, so parts per million and parts per billion, parts per trillion are utilized in industrial processes and in measuring some sort of analytical data. So in this case, parts per million, parts per billion, and parts per trillion are taken and measuring the purification of water as well as purification of air as well. So here, if we take water, let's suppose water, if we consider there is 1 ppm of impurity in water. So 1 ppm of impurity in water basically shows that out of 1 million particles of water, there is one particle of impurity present within the water. So this is how we consider as parts per million. And example of this, let's suppose if we have, we can take the example of this as, when if we have 1 if we have 1 decimeter cube of water, 1 decimeter cube of water is there. If we have 1 decimeter cube of water, then out of this 1 decimeter cube of water, if there is the 1 milligram of impurity would be considered as, if there is 1 milligram of impurity present within 1 decimeter cube of water, that would be considered as parts per billion. Likewise, if we take the example of parts per trillion, we are going to just, to put the power of billion. Billion is having 9 zeros, so we are going to take billion. So in case of billion, we'll be having amount of solid divided by amount of solution into 10 is power 9. And here we are going to take 1000 decimeter cube of water, because there are 3 zero added, like, right? And again the condition would be same. Out of 1 milligram of impurity, out of 1000 decimeter cube of water, 1 milligram of impurity present would be considered as parts per billion. If we talk about parts per trillion, then again there would be power of 12, such that parts per trillion would be having amount of solid divided by amount of solution into 10 is power 12. And here it would be ppt, parts per trillion, and it is the smallest unit of concentration, smallest unit. And in this case we are going to take 1 microgram of impurity present within 1000 decimeter cube of water would be considered as 1 parts per trillion. So this is all about today's video. Hopefully we'll meet again in another video.